Welcome, Doctor.
Hey, how you doing?
Good, thank you. We've just opened the room a little bit early to give people a chance to find a seat, make themselves comfy. How's your day?
Busy but good.
Well, busy is good, and good is good.
hmm
What part of the world are you in?
I'm sorry, can you hear me still?
Yes, I can. Heard. Helpful.
All right, one more time. All right, can you hear me okay?
Oh, that sounds great. And then I can introduce you to Jamie. Here.
Hello everyone.
There we go. Dr. Henri, how do I pronounce your name, your first name?
First name is pronounced Ashegun.
Ashigo, nice to meet you. I'm Victoria, and here's Jamie.
Very nice to meet you, Dr. Henry. Thank you so much for joining us today.
Yeah, no problem.
I was reading some of your paper. It's actually quite exciting. Looking forward to this a lot.
Oh, thank you.
I even was looking up some of the terms. I'm sure some of them will be answered in the talk. And so I'm going to hold them all till
Okay,
then.
no
How
problem.
are you
Yeah,
today?
I'm doing pretty good. Doing pretty good. I haven't used Clubhouse in well over a year, so I'm just kind of getting acclimated to how this all works.
Oh, you're the first one that we're pulling back in then. Most of the speakers have never actually used the platform before. Does it seem much different since you remembered?
Yeah, it seems about the same. I'm just trying to figure out settings wise. I'm sitting in my car and trying
So am I.
trying to trying to make sure it doesn't kick in and it switch over. I'm just trying to figure out where to manage that.
Oh, to Bluetooth?
Yeah.
Right.
Yeah, it does seem to have a bit of a mind of its own sometimes when something just takes over and says, "Hello, we're going to use your headphones now."
Okay.
So it looks like Katarina is going to be a few minutes late, but we welcome friends. Come in. We're so happy to see you. Make yourselves comfortable. We're really looking forward to this talk. I, like Jamie, had to do a bit of Googling, but that's part of the beauty of Science Society, keeps us learning.
So this is a group you've created on Clubhouse that has, I presume, regular meetings around different topics.
Well, I have to say, Katarina has formed this. She is to blame and to to honor. And then we've come together, the team of us, to promote and to sustain the mission of bringing science to the people. And she's been inviting guest speakers, like you, on the cutting edge of their field. And then we also have, there's also a vision that Katarina has, and we share and try to work toward, that has to do with bringing science to the forefront and making it more accessible to all people. So that's a little bit about who knows where we'll be. It's also, Science Society exists also on Discord and YouTube, and there's a blog as well. And Jamie is now going to be a regular contributor to the blog. Do you want to mention that, Jamie? Your new blog posting? I think it's pretty exciting.
Oh, sorry, I was muted this whole time. I was talking. I hate when I do
Are
that.
you learning the
Um,
platform,
uh,
Jamie? Just kidding. Just
and yeah, I was going to say Victoria's quite right. How Katarina's essentially the North Star, and we're all the constellation that surrounds ourselves around this kind of vision she has. Um, so she's been very good at evoking the kind of science passion in all of us to listen to so many different types of speakers. It's been truly phenomenal. And yeah, we're trying to expand it and give more opportunities to spread like basically your work and everybody else's work who comes and talks here. And part of that is I'm starting to dip my toe into putting notes out in the blog form, you know, for the people that don't quite have the time to at the moment to listen to the whole replay. Um, so yeah, so it's quite exciting. Especially get the chance to speak to people like yourself who are working on some truly incredible stuff. I feel like I get to be at the forefront of something. It's very exciting.
Yeah, I think so. So the audience is the quote unquote lay audience. No scientists or specialists. Just
There is some scientists and specialists here. It is a bit of a mixed bag though, so you will have any questions from being complex, detailed ones to more layman. I'm on the more layman's end of the spectrum myself, but others will be here who do have a much more detailed understanding.
like Serena.
Yes. Yeah,
Serena.
welcome. I'm very
Aha!
curious on this topic.
Henri, Serena.
Um, yeah, the efficiency of 40 is very impressive. Chemistry is my background, so I'll be interested in your talk. But yeah, it's a fairly wide range of people that attend. So
And I have to say that the replays are in addition to people who've missed the room, we hear that a lot of people go back and listen. You know, like the first time's for fun, and then the next time you maybe take notes. So, you know, or guests have used the replays as well as part of, you know, their own promotion.
okay, I got it. Interesting. Let me apologize in advance if like I said, I'm sitting in my car while my kids doing
No,
regular activity. So if there's some noise in the background, I apologize in advance.
oh,
We
no
love that.
problem at all.
Yeah,
Yeah,
that's real life. That's why we're saying
yeah.
this is we're bringing science to, you know, to, oh, sorry, wait, that's a horrible sound. Yeah, bringing science to the community at large, and, you know, scientists and non-scientists, but just, you know, enthusiasts of knowledge. And we've had several guests who've had their children in the background, and that's life. That's
The,
great.
the,
Your
the,
kids get a
the,
great
the
example.
their 3-year-olds are technically now Science Society contributors then. So it's been totally fun and we love it. And like Victoria said, this is real life, you know. And we're actually quite relaxed here, as much as we're all excited on the details of the science and what you're describing to us. And we're also we try and be as a relaxed bunch as possible, because science is supposed to be fun. It's supposed to be interesting. It's supposed to inflame our curiosity, not shame us for not knowing things. At least that's how I'm taking it.
That is the spirit.
Mm.
How old are your children, if I might ask?
11, 10, and 5.
Oh, fantastic! So I imagine that they're all some enthusiasts, like photovoltaic enthusiasts among your family, or disciples.
My son, my 5-year-old, likes to say that he's the king of solar panels. So his thing right now is whenever we're driving around, if we see solar panels, he gets excited. Then point
That's
them out.
awesome. He must have an incredibly interesting show and tell at school. Do they still do that in schools? Do they still have the show and tell where you bring something in?
Yeah, if he does show and tell, he usually takes his little cars and little men, little action figurines. That's the level he's at right now.
Right, well, wait till a little bit further when he can bring in. This is an advanced solar panel that's going
Yeah,
to resolve global warming problems.
yeah.
Welcome, Katarina.
Thank you so much. I really apologize. I usually am never late. Usually time is up, but today I apologize for being late. Thank you so much for coming. We really appreciate it.
My pleasure.
What did you chat about?
Kid.
Oh,
Were
we were talking
you
about kids. And we
oh
were
kids?
trying to fill Dr. Henry in about Science Society and a little bit of the background of what your vision and what you created and what our hopes are.
Oh, nice. Thank you for doing that. That's wonderful. Really appreciate that. And yeah, did we?
So I think we can get started. Do you want to?
We didn't do the
Yeah.
bio. We didn't do it. That's saving for you.
Okay. Okay. Cool. Okay. Let's start then. Gilbert. Hi, Gilbert. You're also here. Welcome. Okay, welcome everyone to the Science Society. Really appreciate everyone coming, but of course, a special thanks for our guest speaker, Dr. Azagun Henry. And let me give you some information about him so that you get to know him a little bit. He did his bachelor in Florida University and his master's at the Massachusetts Institute of Technology, and also his PhD at the Institute at the MIT. And he is actually, he began Georgia Tech to have his own lab in spring 2012. And he previously has worked as a postdoctoral fellow at the Oak Ridge National Lab and Northwestern University. He first started out working on modeling controller performance for earthquake mitigation in high-rise civil structures. And with this background in studying how buildings react during earthquakes to the vibration, then he moved on to studying atomic vibration with molecular dynamic simulations to incorporate an interest in heat transfer. And then after gaining that experience with classical molecular dynamics simulations, he then began to incorporate first principles calculations and quantum molecular dynamics simulations. So yeah, his research is mostly about heat transfer, combustion and energy systems, and renewable energy technology development, solar thermochemical hydrogen production, and so on, like a lot of principle and modeling techniques around this area. So we are very honored to have you here, especially as such an accomplished researcher in this very important field with in the midst of climate change. So thank you so much for being here. And if it's okay, Victoria usually asks general questions first about you as a researcher, and then the stage is yours for your talk. Thank you.
Okay. Yeah, thank you for having me. Yeah, it's helpful to know a little bit more about the format. So it sounds like you said Victoria's going to ask me some questions, and then it sounds like you're expecting that I'll, I guess, give a talk for how long? How many minutes do you want me to talk for? And then I guess is there a Q&A for that or?
Yeah,
It's totally up
exactly.
to you. Yeah.
It's about, did
So,
you say 12 hours, Eric? Is that what I heard?
so no, so it's really up to you how how much time you want to offer us. So as long as we have enough time for some questions, the talk can go as long as you wish, like as short or as long as you wish. But
20 to 30
I
minutes is
think it's good
the
to have
average.
some.
Sorry, so, I beg your pardon, Katerina. I beg your pardon that you were finished.
Yeah, so it's really what you would like to, the main messages you would like to tell us, and that we then still have time for some questions. So thank you.
Oh, Katerina, do you have the link for the slides to put on the
Yeah,
top?
I'm on it. So while
Okay,
Victoria
good.
is asking the question.
All right, settle in. Everyone's here. Everything's fine. So again, welcome, Dr. Henri. Science Society is really excited to have you and hear what you have to share with us. And just to give a little bit more of a personal perspective, beyond sharing your work, we like to familiarize our audience with a bit more of the person who's here. And so my question to you is about your background. If you can think back through your life, even to your childhood, and think if there was a moment or an experience during which you felt a particular connection to science, where you felt like, okay, this is something that I feel really interested in, and maybe you can tell us about that.
That's a pretty good question. So there is a turning point for me. That was senior year of high school when I took calculus. I would say after taking calculus is when I actually knew that I wanted to be an engineer. And what the turning point was the teacher that I had was a really, really excellent teacher. He himself was an engineer, had an engineering background, and thankfully for me was teaching high school. And he did a really, really good job of. He had an interesting style of teaching, which is that he would really take an extensive amount of time to talk to us about why a particular topic we were going to learn was important, why it was interesting, what we would be able to do with it, and giving some perspective on how it's useful and what you can apply it to before he actually taught us what it was. So that, I never forget, he taught us before he taught us what the derivative was, and he hyped it up for I feel like almost an entire week, and he just kept going on and on about, once you learn this thing, you'll be in the less than 0.1% of the world that knows what this is, and once you learn this thing, I'm going to teach you, this is one of the most important things you need to be able to put a person on the moon, and he just kept going on and on and on about what you could do with this thing. And for me, we by the time he got to it, we were just salivating, like, well, tell us what it is, man. And just keep going on about it. And so once he finally told us, I will remember. I remember he did a example problem where it was something about like a company selling hamburgers or something like that, and the point of the problem was to determine what is the optimal selling price for the burgers so that you maximize profit. And he showed us, like there was some sample data, and he took the derivative of the function and he was able to set it equal to 0 and solve for what is the optimal price to sell the burgers at. And at that moment, it all kind of clicked for me. And for the first time, math became something that was useful and like might actually make you money. And that got me very much interested in what else you could do with math. And at that moment, all the math that I had taken up until that point all suddenly had meaning, like it had utility. And before that, you kind of just do math and they just tell you solve for X, solve for this, and you don't really know why you're solving for it. It doesn't really translate to any physical meaning or any purpose. And once I took calculus, then I could actually start to see what the purpose, what the functionality and the utility of the math was. And that, of course, then that mapped on to science, and then it was kind of clear that connecting math and science together was pretty powerful.
Thank you. I'm just navigating back to where we are. I'm always taking notes, and because these words are so precious, everyone has a different experience, and I'm wondering if that's influencing the way that you teach your children or the education that you're seeking for them, so that they have that opportunity to hear what's important. The reason. That's what you always hear kids asking in a class is, why do we have to know this? And your high school teacher put that first at the front. It reminds me of when I took calculus, and I was astounded. I did horribly in that class, but I loved it so much, and I thought, this is what we could be sharing with very young children instead of torturing them through arithmetic and memorizing times tables. But kids are so conceptual, and you can be conceptual and have understanding without memorizing 25 times 37 and a half. So that's really, thank you for sharing that. And so from that point, can you bring us along the path that brought you to your current work now that you're about to share with us?
Yeah, it's a pretty long path. So from high school, I spent my first summer doing some actual engineering work. Worked with Professor Makola Abdullah at Florida A&M. That was a uh, very big catalyzing experience. Never will forget it, and it is will forever be grateful for the opportunity he gave me. I mean, he took a chance on a high school student, a recent high school graduate, and let me work with his graduate students on a project. And this was before any of these kinds of ideas or doing these kinds of experiences was a popular thing. So he was very early on willing to take that risk on me, let me do a project with them. I got a ton out of it, and what came out of it, I ended up being included on a conference paper that helped separate me from the pack when I went to the career fair. That led to me getting an internship as a freshman, and kind of again separated me from the pack. I was kind of on a fast track to be able to do more things than my peers, really because of that initial experience that he gave me. That gave me, just looked like one extra line on my resume, but that one line was a really big distinguishing factor. And so that kind of catalyzed a lot of things for me. I spent time, went and did a internship at Visteon Automotive for a summer, and then ended up going back to work with him to do a summer of research. Got to spend a summer in Japan, in Tokyo. Then I came back, and then the next summer, um, I ended up going to MIT to do research with who would later become my PhD advisor. Spent a summer with him. That was critical because that ended up leading to me getting a letter of recommendation from him um, for graduate admissions the next cycle. I believe that probably is what played the most critical role into getting me into MIT. Got into MIT, ended up working with him, did my graduate degree with him. Got into an area very early again that was kind of nascent at the time, but it was an area that I was particularly fascinated by. When I went to his office after being admitted, spent another summer with him. And when I first got there, he was just like, so now that you're here, what do you want to work on? And it's kind of interesting in that moment. I had not really thought it through. I just said what was first thing that came to my mind, which I was very fascinated by the question of what exactly is temperature. I had felt like I had not gotten a straight answer when I was an undergrad. I was really curious what it was at a very fundamental level, at a very physical level. Like, what is it, and why does it have its own units? Why is it? Why can't we? I'd heard the saying that it's related to the average kinetic energy of the atoms, and I just could not, for the life of me, understand why we don't use the same units as energy then to describe it. And so I was, just scientifically curious about that. I told him I was interested in how atoms move, how they vibrate. I was curious how fast they move, what frequencies they move at. He said, well, I don't necessarily do that kind of research, but it's called molecular dynamics, and here's a book, and you can go figure it out. And that's kind of the quintessential thing that happens for MIT students is you give them a little bit and then you let them run with it. And so I was fortunate enough that he let me do that. I got some fellowship support the next year, which gave me the freedom to keep working on it. And then that allowed me to kind of carve out my own niche scientifically in an area that, again, was pretty nascent. There was really only me. I was kind of like the second or third person in the United States that was doing that kind of work. There was a number of people that had been working on it in Japan previously, but was one of the early adopters here in the United States, and got involved very early. Developed some expertise. I got through graduate school, got a job at Georgia Tech as a professor, and then I deferred my position at Georgia Tech for 3 years. I ended up going to Oak Ridge National Labs to do a postdoc afterwards. This is where I started learning how to do first principles calculations. So I was doing molecular dynamics, studying heat transfer at the atomic level. Um, Around that time, first principles calculations were becoming more proliferated. Um, And so I wanted to learn how to do them, and went to do some postdocs to facilitate that. Spent some time at Oak Ridge. Then I went to Northwestern, and then really started to get finally back to my original passion, which my original goal and passion from the beginning was really to do something in energy at large scale, not just atoms and studying science. And so an opportunity came to work at the Department of Energy at the Advanced Research Projects Agency for Energy, ARPA-E. Got a fellowship with them, and that was, I would still say to this day, probably the greatest work experience I've ever had was at ARPA-E. Complete eye-opener, complete game changer for me in terms of what I learned and how quickly I was able to get up to speed on totally different areas that I knew nothing about previously. And that expanded my scope and got me focused on really solving real world problems, and got me interested in trying to do some experiments and become an experimentalist and develop technology. And so once I did that, I ended up going to Georgia Tech, starting my job there, developed an experimental wing of my research, and got some funding, had a couple big projects, and kind of carved out my own niche in terms of energy and heat transfer, and specifically doing heat transfer at extreme temperatures using liquid metals, using ceramics as an infrastructure as opposed to metal-based infrastructures. And those were kind of radical, I guess even still somewhat radical ideas. It was a very different way of thinking, and it worked out, paid off, and has been paying lots of dividends. And then started getting recruited to come back to MIT, and it was a very difficult decision. I was very happy at Georgia Tech, but ultimately ended up deciding to come back to MIT. Things have kind of taken off even further from there, and we've published a couple of big papers. And now, the research from essentially a decade ago is now distilled down into two technologies that we're developing in my lab now. One is what we call thermal batteries, or thermal energy grid storage. This is a energy storage concept that um, is essentially a large utility scale rechargeable battery system. And then there's another technology we're developing, which we call methane pyrolysis. Both of them make use of a particular breakthrough that happened when I was at Georgia Tech, which is we developed the ability to pump liquid metal at extremely high temperatures, far above 1,000 degrees Celsius. And so once we did that, that kind of opened the road for us to be able to do all kinds of new things. And those are the two big ones that we're focused on right now.
Wow. I'm writing all this down, and it's
Wow.
an amazing playbook. It's just an amazing playbook at how to how to get where you are, how to follow your motivation, also how to empower others to to do what their calling is in the world. And also I think it's a really great lead in to the rest of your discussion. And kind of, I don't sometimes when you're given an experiment to do when you're just in high school and you don't know what the background is or the why, it can be sometimes like that with listening to a talk. So now we have background to what led you here. So thank you so much. And as Katarina was explaining, it's entirely up to you to deliver the body of your talk, and then afterward, if you'd like, well, then we have the Q&A. I think that you would prefer it that way. Sometimes guests prefer to have the questions along the way to push their talk along, but it's completely up to you, and we are all here to assist you and take care of the room and whatever questions come up in the chat, and also bringing people up to ask you questions as well. So we're here to serve you, and we appreciate you being here. So please know that the mic is yours.
Okay. Yeah, I'll probably keep my talk pretty short, maybe 5-10 minutes, in hopes that maybe the majority of what we go through will be via question and answer. So, I mean, the title of this room is Thermophotovoltaic Efficiency of 40%. I'll just put some context around what that means, what that is. So this sounds like was largely sparked by a recent paper we had that was published in Nature. It demonstrates a critical component to this technology I mentioned called thermal batteries. The technology, thermal batteries, I'll explain how it works, and then you maybe understand the significance of this advance. So I guess we're coming up on maybe 5 years ago is when the first Nature paper was published. We had another Nature paper where we demonstrated pumping of liquid metal at 1400 degrees C that set a Guinness World Record, and we got a significant amount of press around that. Even in that paper, we mentioned that we were already thinking about energy storage. Later, maybe a year or so later, we published another paper, which was published in Energy Environmental Science, showing a whole system that we envisioned for how you could make use of this ability to now pump liquid metal at extreme temperatures, to now make new systems. And let me maybe step back and give a little bit of context why the liquid metal pumping thing is such a big deal. So, excuse me. So the reason the reason it's so critical is because the majority of what we call thermal fluid infrastructures, meaning the way that energy is moved from one place to another in chemical plants and power plants and generally various technologies at large scale, is you have some kind of medium that's moved. In some cases it can be solid, many cases it's gas, and in some cases it's liquid. And moving the energy around generally means heating something up from one temperature to the next, and in doing that you end up putting energy in to heat it up, and you carry that energy by pumping the fluid or moving it from one place to another. Liquids are ideal in many cases for these pumping approaches, because gases are 1,000 times less dense than liquids, so you get 1,000 times higher density of the atoms. You're essentially containing the energy and the kinetic energy of the atoms, so it's much more dense to use a liquid. And the problem is that when you start to think about what temperatures you can do this at, um, very quickly you run into some important limitations. So one of the most important industrial infrastructures that's been pretty widely proliferated is the use of molten salt, or so liquid salt. They use sodium potassium nitrate, eutectic, um, in concentrated solar power. There's about 100 of these plants in the world right now. These plants basically take light from the sun, use mirrors to reflect that light up to a tower or to a central location, and then they have an absorber, something that absorbs really intense sunlight and heats up, and then they cool it with liquid salt. And now, so I say cooling, meaning they're removing the heat. The object is hot, but they're transferring that heat to the salt. And so they have two tanks. They have a cold tank and a hot tank. The salt is liquid in both tanks, and they just basically take the cold tank of salt, pump it up to this tower, heat up the salt. It comes down at a higher temperature, and they put it in a hot tank, and they store it. And so this approach is used to store energy at very large scale, and it stores it thermally. And the problem with this technology is just that it's not cheap enough. And one of the ways to try to make it cheaper is to make it more efficient. And to make it more efficient, ideally you want to operate it at higher temperatures. So the higher the temperature, there are two laws of thermodynamics that govern everything that we do. The first and second law, and there's a second law. The second law places a very severe limitation on what you can do with heat. And what it does is it basically makes a statement about entropy. And entropy is interrelated with heat. And the temperature at which you have some heat ultimately governs how much entropy that heat has. And so, because you can't destroy entropy, when you try to convert heat to another form of energy like electricity, or thermodynamically we call it work, there's you can convert some of the energy, but some of the energy has to carry out the entropy as well. You can't destroy the entropy, so that restricts you from being able to convert all of the energy from heat to work. Because what's special about work is the one form of energy that doesn't actually have entropy associated with it. So you have some energy that also has entropy. You want to convert it to another form of energy that has no entropy, but you can't destroy the entropy. So another form of energy, heat, has to carry out the remainder of the entropy. And so that sets a limit on what fraction of the heat can actually be converted to work, because you still have to conserve the entropy at the bare minimum. And so this places a limit on efficiency. And so the hotter the heat is, the less entropy it has associated with it, and therefore the larger fraction of it that you can convert to work without having to waste some as wasted heat or heat that you discharge back to the environment. And so ideally you want to push temperature as high as you can, but there's some practical limits that come into play, and the most severe practical limit has to do with corrosion. So when you try to heat something up, generally most chemical reactions that take place all get faster the hotter something is. So the hotter it is, the faster the kinetics of the reaction, generally speaking. And so when you talk about corrosion, you talk about heating something up, beyond, let's say, 500 degrees Celsius or 600 degrees Celsius. Reactions start to get very fast, and corrosion starts to happen very fast. And ideally, what we wanted to do was push the temperature up beyond 1,000 degrees Celsius, far about beyond 1,000, so that things could be very, very efficient. And the problem you run into is corrosion, and so it's very difficult to find compatible materials, some kind of material you can hold the liquid in as a solid. So you need like some kind of solid piping infrastructure, some kind of solid to use for the pumps and the valves and everything else that's going to touch the medium, and those materials will get corroded by that liquid. And so we essentially came up with a different idea, which was to choose materials from the beginning. Or let me take one more step back. The typical thing that would happen is mechanical engineers would sit down, design a system, and say, okay, let me call up a material scientist, and here's my system, here's my requirements, tell me what materials I can possibly use that can operate at these temperatures and under these conditions. And doing it that way was kind of a losing proposition. If you wanted to go temperatures, generally speaking, people would define a system that was so difficult to find materials for, it was essentially intractable from a cost standpoint to find any materials that could last and survive at the temperatures of interest. And so we decided to flip the problem around and do it a different way, which was start with the materials first and figure out which materials can actually function in these temperature ranges, and then figure out how to solve the mechanical engineering problem second, and figure out how do you make a system out of these materials. And so what we very quickly settled on is there are materials that can last and that can survive at much higher temperatures, well beyond 1,000 C. Those are ceramics, and these materials are generally very brittle. Brittle meaning they don't bend, they generally just crack and break. And that's not ideal. It's not the kind of materials that mechanical engineers would like to use. We prefer things that fail gracefully, that'll bend and fail in some kind of gradual manner rather than all of a sudden catastrophically. And so it's not the favorite of mechanical engineers to use brittle materials, but it is also not impossible. And so what we did is we basically figured out that you can use materials that are brittle, that have all the thermodynamic properties that we want, in the sense that they stay solid, they stay strong, and they don't corrode, with the materials that we're interested, which turned out to be liquid metals, which have a huge range of liquid behavior where they don't boil. And we started settling on the right materials, and then the key was, how do you make a pump? How do you connect two pipes that are made out of ceramic? How do you make flow meters? How do you make valves? How do you make all these components that are straightforward to make if you're talking about metal? But when you now talk about making them out of ceramics, it becomes not clear how you'd actually make those things. And so that was our big contribution 5-6 years ago. That's how we demonstrated pumping liquid metal at an extreme temperature, where we invented, essentially new kinds of seals that you can use. The sealing problem is not very sexy. It's difficult to imagine that you'll get a very high-profile paper inventing a new seal, but we were very lucky, and I think very appreciative to be able to get some recognition with that paper published in Nature. And once we did all that, then that kind of opened up the world, and it was like, it's possible now to pump liquid metal at 1,400 degrees C and hotter. So now what can you do with that? And so there are two technologies we're developing. I'm just going to focus on one. One I mentioned earlier is methane pyrolysis. If anyone's interested, I can talk a little more about that. But the main one we're focused on now is energy storage. And so, we make our system essentially entirely out of graphite, carbon. Carbon is good till about 3,000 degrees Celsius. And so we devised a whole system that basically can store energy at extremely high temperatures, uses liquid metal tin as the heat transfer fluid to move the energy around from one subsystem to another. And we can pump it, we can valve it, we can make pipes, we can make joints that last, that don't leak liquid metal. And so those are the kinds of systems we've been building in my lab. Now, the key question, when we get to thermal batteries, the way it works is we take electricity, excess electricity. The main problem we're trying to solve here is that you have solar during the day when the sun is out, but once the sun goes down, you won't have renewable electricity. Wind, you don't know when the wind is going to blow, so we don't have great forecasting. And point is, you don't get the wind blowing or the sun to be out exactly when you want to use the electricity. So you need the ability to buffer it. You need to be able to store it so that we can use it whenever we want. That is how the utility grid is set up. It's set up where they try to predict how much electricity is going to be used in the next hour, and they dispatch the turbines and the power plants to produce exactly how much electricity they expect people to use. And so it's made to use, and there's no real buffer. There's not really any storage on the grid now. It's not held anywhere. So the 60 hertz that you have at your AC outlet, that frequency, 60 hertz, that's the same exact speed the turbines are spinning at. They're literally synchronized with all the electrical outlets throughout a city. And so there's no buffer in between. There's no storage that's holding anything in between. But now that we need to switch to renewables, we need to create a means of storing the energy in between. So the idea here with thermal batteries is you take electricity off the grid. When you have excess, let's say during the day when the sun is out, you have more solar power than you have demand on the grid. So during that time is when you start charging up your batteries. And so you use that excess electricity from from solar to run resistive heaters. So what we basically do is we run a heating element that's just like an incandescent light bulb filament. So it runs at about 2,500 degrees Celsius. That emits a bunch of light. That light is transferred to some piping. The piping's made out of graphite. And in a sense, our entire system's almost made out of carbon. That graphite tubing has liquid metal tin flowing inside of it. The liquid metal flows past that heating element, heats up from 1900 C to nominally about 2400 degrees Celsius. So from glowing white hot to even more glowing white hot. To put these temperatures in perspective, 2400 C is about half the temperature of the sun. So it's extremely hot. The entire system is held inside of a warehouse that has inert gas in it. So none of this system is seeing air because graphite itself would oxidize, would turn into CO2, would burn gradually. It won't catch on fire, but it would gradually oxidize. And so the liquid metal is then routed over to the storage bank, which consists of very low cost graphite blocks. We heat those blocks up to 2400 C, and once the blocks are all at 2400 C, that is now where the thermal battery is essentially charged. Just to give you a sense of scale, you're talking about a giant bank of graphite blocks that are nominally about 10 to 20 feet tall and extend. There's thousands of them, so they extend like about half a football field, and they're all glowing white hot. And so that's where all the energy is stored. Then when we want to discharge back to the grid at night or whenever people want the electricity, we pump the liquid metal through those blocks, retrieve the heat. So now you got a continuous stream of 2400 degrees Celsius liquid metal. And we feed that into what we call a heat engine or a power block. This is where this new paper on thermophotovoltaics comes in. So normally if you want to convert heat to electricity, the way you do it is you use a heat engine like a turbine to convert heat to electricity. Instead, what we do to be both cheaper and fast with a faster response time, we convert the light coming off the piping infrastructure. So since everything's glowing white hot, we actually just put special PV cells next to the piping that consume some of the light. And in the course of consuming that light, converting it to electricity, which then goes back on the grid, the liquid metal will start to cool down. And so it comes out of the system. The power block at 1900 degrees C gets pumped around to the graphite blocks and gets reheated back up to 2400 C. So it just circulates around. There's no consumption of any materials. The only things that come in the system are electricity. The only thing that leaves is electricity. And the rest of it is basically just all held inside this inert warehouse. And so what's special in this paper on thermophotovoltaics is the efficiency. So the efficiency is the measure of how much electricity is coming out divided by the amount of energy we've consumed from what would be that liquid metal. And so what fraction of the energy that came out of the liquid metal got converted to electricity. And so we set a new world record for that at 40%, actually 41%. Reason that's significant is because the idea, which this kind of photovoltaics, we call it thermophotovoltaics or TPV, for a very particular reason. The way the efficiency is defined is different than normal photovoltaics. And the other key piece is that these are photovoltaics that are more so set to use an infrared light source rather than visible light like we normally do with solar PV. And so the key distinction with thermophotovoltaics is the source of light is a terrestrial object that's hot, rather than the sun. And and then that energy gets converted in the cells. A very key aspect of these cells is they are made with a mirror on the back, and this mirror reflects a bunch of light that's actually not converted in the cells, sends it back to the hot infrastructure, preserving it so that we don't lose it. And so in this paper, we demonstrated a new efficiency record. These cells, this kind of technology has been around since the 80s. There was a paper back in, actually a little bit before I was born, back in the 80s. And Dick Swanson from Stanford, he's a professor that started SunPower, one of the big solar PV manufacturers. And he tried this idea out. He had a heating element at 2000 degrees Celsius, and he managed to use silicon PV to convert at 29% efficiency. And that was the world record for about 40 years. People tried a variety of different materials, made a lot of improvements. But the key point was that the temperature of the light source was much lower, down at 1200, 1300 degrees Celsius. And so what we did is we pushed the temperature back up, redesigned the PV to operate with higher temperature heat sources, and now demonstrated that the efficiency, with lots of advances that have happened over the last 40 years, now is at 40%, and we have a path to get to 50% with some additional improvements to the mirror reflectivity. So I'll stop there, take any questions that folks have, but that's the basic way the system works. And this latest paper was really about the new record on efficiency for the TPV.
So, from the experimental design, how would that translate to an application? Because I understand that it's kind of a very specific engineered scenario that we're looking at, but in what situation would you want to capture the energy, or are there multiple examples?
Yeah, I mean, I would say the main example we are trying to aim for is where you have, yeah, let me maybe give a little context to this. So right now in places like Arizona, California, Nevada, also in Germany, they put up too much solar photovoltaics. They put so much up that now it started to destabilize the grid. And so they actually pay other states, and they throw away a bunch of the electricity. It gets curtailed. They throw away solar electricity because they can't use it all, because it destabilizes the grid. And so it's a very important point I was raising about the synchronization between the AC outlets in your house and the turbines. So if you've got a resource on the grid that's providing a lot of electricity, and if you look at the way solar photovoltaic output comes out, it fluctuates. If a cloud comes by for a couple minutes, starts to block out the sun, then you get a big dip in the PV output, and it would cause all kinds of blackouts and brownouts. And so, what typically happens is utilities, they put up big PV installations or big wind installations, and then across the street they put up another fossil fuel power plant to back it up, because the electricity that goes on the grid is not reliable enough to keep the grid stable. And so it's, even though there's a lot of PV, there's actually um, the electricity from fossil has not really started to go away yet. And so the purpose of this system is to actually store the electricity you have during the day when the price goes negative, or when the value of renewable electricity is low. When you can't use it directly on the grid, you use it to charge up this battery, and you store it and use it later. So basically, you're converting electricity to extremely high temperature heat so that you can use it later. And storing heat is 10 to 100 times cheaper than storing it in an electrochemical battery like lithium ion. So storing heat is very cheap. That's the main reason to do it.
Oh, okay, because I was thinking perhaps something uh, like space travel, where we might want some sort of heat shield. Could this act in that sort of fashion, or is the symmetry of the problem very particular to the setup? Because I know you said you went from materials to design, which is already crazy to me. Like, I don't know how you start backwards is how I think about it, but like totally awesome. but to think about how those different design, like I would not know how to do it using anything other than a procedural algorithm that would just run through permutations. Maybe you could comment on the process of how we could perhaps come up with a different application, or is this just like in your opinion, perhaps this one application is the application?
This is likely the biggest impact implication. So maybe to put that in perspective, there'll be other applications, but they will be dramatically dwarfed by the impact of solving the electricity storage problem. So to put it in perspective, roughly 20 to 25% of global CO2 emissions come from electricity production. Another 20 or so percent, 15 to 20% is associated with transportation, mostly driving cars and vehicles. So this one technology, if it's successful, I just started a company, and so if we were able to successfully commercialize this, what it would do is that it would allow us to put up more PV and wind and actually start shutting down fossil fuel plants and reducing the CO2 emissions associated with the stationary power sector or the electricity sector. The reason that's significant is because if we can fully decarbonize the grid, then you can switch to electric vehicles and charge those vehicles from a decarbonized grid. So you can ultimately decarbonize both sectors by just inventing one technology, which is energy storage. I mean, PV and wind are already cheap enough. The real issue is storage.
Yeah. Like here in Canada, they're planning on shutting down a bunch of the plants, and that mean like the solar panel hasn't been as successful. The nuclear power, people are paranoid. So then all you have is natural gas. So we're expected actually to increase our carbon footprint by 300% over the next decade, which is like expletive. So if you can get this going sooner, I would love it. Because I think this is like a surprising thing, the cost of energy. I think a lot of people miss it, or even the consistency. Like I myself recently had to get a UPS with a power conditioner because my power is not consistent, and running simulations or the GPU, it tends to crash, and then you get some weird anomaly about kernel power in the processor. So it's a very, I guess, important and ubiquitous problem that many of us perhaps miss.
Indeed, yeah. I mean, the if we solve the electricity problem, which I think will take 20 to 30 years, the next problem we would be focused on is industry. I mean, we'll do both in parallel, but industrial heating and usage of fossil fuels is the next biggest problem. That's about 15% of global CO2 emissions, and that's relegated to a couple of applications. Biggest one is cement production, second is steel, and third is aluminum, and then hydrogen is around 1 or 2%. So it's a couple of major industrial applications, and we essentially have to electrify them. We have to actually, they burn fuel in many cases. A big portion of the energy they consume is in for natural gas and coal as a heat source to then run their industrial process. And so we have to find ways to actually electrify them and have them use either high temperature heat directly from our process or electricity provided by the grid to provide the heat for their process.
Awesome, thank you. Anyone else or whoever is next, please go ahead.
Go ahead, Abyss. I saw you flash your mic.
Serena, hi Sagun. Great presentation, great work. I actually was not aware that it was your lab that was producing this, but I was made aware about these kind of batteries, which was really fascinating for me because like I do have a chemical engineering background, but so I do have like a few questions for you. So I'm kind of curious what sort of like the heat capacity of those molten the molten alloy is that you used in the storage system. That will be my first. And also, if you have a different kind of heat exchanger design to essentially facilitate or maintain the temperature, um, that I'll be really interested in doing that. And lastly, I was kind of interested to know if you actually explored using these kind of storage with energy systems or energy production systems that actually operate at higher temperature. And for me, personally, when I think about it, geothermal and nuclear actually come to mind. So, have you considered how this kind of storage can be used in tandem by sort of like leveraging the spent heat from these kind of energy productions to essentially maintain the battery?
All right, yeah, let me try to remember your question. So the first one was about, remind me again.
Oh, it was heat capacity of
Oh,
the.
heat capacity. Yeah. So let me deal with that one quick. That's pretty quick. Um, so one of the things we talked about earlier, I study heat transfer at the atomic level, and so um, from my perspective, the physics perspective, essentially the heat capacity of everything is the same um, on a per atom basis. So, what heat capacity is essentially a measure of how many bins, how many different degrees of freedom you can store energy in. And for every atom essentially has 3 degrees of freedom. It can move in X, Y, and Z. So if you can go look up a bunch of data. If you plot the heat capacity of every element in the periodic table on a molar basis, it's about the same. So, and it's about 3 Boltzmann's constants per atom. Um, so that's that answer. I mean, for liquid tin, it's about, I think it's 210 joules per kilogram per Kelvin. Um, that's the liquid. The actual storage medium, graphite, is more like 2,000 joules per kilogram per Kelvin, but that's just because of the mass difference between tin and carbon. So tin is a heavy metal, so a lot more kilograms per atom, and so seems like a much lower heat capacity, but on a per atom basis, it's similar.
Yeah, so the reason I asked is if there's a direct correlation between the heat capacity and their ability to store electrical energy or generate electrical energy.
Yeah, yes and no. I mean, so since the heat capacity of basically everything is almost the same, that's not really what we design for. The main thing that drives the design is the cost. So the question then becomes, what's the cheapest atom you can buy? Because what we care about is dollar per unit heat capacity. And since the heat capacity of virtually everything is almost the same, what we then care about is dollar per atom. And so carbon is one of the cheapest atoms you can get on Earth. But there are others that are even cheaper. Steel, iron is cheaper. Aluminum's pretty cheap. Zinc is very cheap. Magnesium is very cheap. Um, silicon is very cheap. Um,
Like I've often heard the phrase, you want it to be dirt cheap, preferably actually made out of dirt locally.
yeah, yeah. So it depends on whether or not you consider carbon dirt, but yeah, it's in that range of the cost of dirt. I mean, silica, sand, and things like that. There are people that are trying to use sand as an energy storage medium. I mean, at some point, so in our case, right, and this is generally the case. At some point, the cost of the medium becomes so cheap, it's no longer a significant cost in the system, and that's the case for us, right? So our cost is essentially about $10 a kilowatt hour. Three and a half of those dollars is the cost of the graphite, the medium. The other $7 or so is the rest of the system. So we could maybe find a cheaper medium. Maybe we could go to iron or something, but it's not really going to help us because we have to build an infrastructure around it, and the infrastructure we're building is really the more expensive part. So we're better off trying to figure out ways to keep that cost low than to just go with a cheaper medium. So graphite's sufficiently cheap that we don't really care to go much cheaper.
Um, so, yeah, my second question is about heat exchanger design. If there's any kind of different heat exchanger design
Yeah,
you're doing, because I would assume that cooling is an issue in this case. You just don't want it to cool everywhere else, and if you don't, even if you have like perfect insulation, you just want to maintain the temperature.
yeah. So do we have new heat exchanger designs? I would say no. I mean, our system design itself is unique. If you could look at our system and call the way we put the heat into the blocks and pull it out some form of heat exchanger. If you do, then yeah, it's a little bit new, but not. I mean, nobody who is in heat transfer would look at it and say it wasn't obvious. So nothing particularly special in the heat transfer portion of it. The insulation we use is very far from perfect. So that's actually one of the most expensive aspects of the system. And somebody brought up earlier about like putting us on a space vehicle. Like, so another key piece of this is that it needs to be very large. Part of what makes the cost low is it needs to be very large, so there's a low surface area to volume ratio. So we pay a lot for the special insulation that we use, which is made out of like carbon fibers, rayon-based fibers. That insulation is expensive, so the bigger the blocks are inside the volume, the less expensive the overall system is for the same thickness of insulation that you put around the outside.
Yeah, my last question was if you can use this in tandem with power stations or power infrastructure that uses high temperature like geothermal and nuclear.
So geothermal actually, despite the fact that lava is pretty hot, 1200 C, geothermal actually operates very low temperature, like 200 C, 2 to 300 C. So geothermal is actually very low temperature. It's close to like nuclear, down in the 300 C range. So short answer is yes, we could, but it would be extremely wasteful. It would be kind of dumb to store energy at 2400 C and then use it all the way down at 300 C. For that matter, you're better off just storing the energy in the blocks at 600 C or 900 C or even 1000 C, much lower temperature to get close to the temperature of use. But it's so although yes, you can do it, these there are applications where it would make sense, yes. But it is not our focus at the moment, just because those applications are much lower impact than just solving the electricity storage problem. But I do anticipate down the line hybridizing and using our storage approach for that kind of thing will make sense at some point. It's just likely not to be the most impactful thing we do.
Got it. That makes actually sense because I was also thinking that maybe we can maintain you can actually play around with the thermodynamic conditions by altering or reducing the pressure to essentially reduce the temperature as well, because even though metals seem to be somehow unaffected by it, but they actually have the tendency to do cold welding in low pressure conditions. So maybe you can, by reducing the pressure, you can actually also reduce the temperature and use that as or at least like that could help you at least like have manageable way to sustain the battery.
Generally speaking, we don't need to tamper with anything like that. I mean, changing the pressure would have dramatic consequences on all kinds of other parts of the system, so we generally keep it right near 1 atmosphere. What keeps the system hot is just the fact that it's so large. So to put this in perspective, right, like the amount of time it takes something to cool down is related to two things: how well insulated it is, and also how big it is. So you put a cup of coffee on your table, that will cool down in about an hour or so, like in that time frame. You put tens of thousands of tons of graphite in a warehouse that's half the size of half a football field, and it actually takes months for it to cool down. So we don't really have the problem of like losing the heat and dissipating too quickly. Like we can hold the heat without input for months.
Got it. Thank you.
So, Mark Weiss, I saw you flash your mic. Do you have a question?
Thank you. So asking this is really fascinating stuff, and it seems like what you're saying is that with your approach, these very efficient solar cells, we don't need to go to seasonal storage batteries based on iron and iron oxide, like Form Energy is working on. Is that right?
I wouldn't say that. I still think there is potentially a place for seasonal storage. Our battery is likely to solve the 10-hour, well, not even 10-hour, I mean, let's say 5-hour to 50-hour regime, which is the majority of what we need. I think that going to 100 hours of storage, doing a electrochemical battery could make some sense. There's another approach that we may use. I'll refrain from going into too much detail, but I'll just say that our battery may have another option to be used with a fuel, a renewable fuel like hydrogen or something like that. So, my suspicion is that how this will play out is we will solve the majority of the storage problem, getting to like 95 or 90% penetration of renewables on the grid. But the last 5 to 10% will require some kind of seasonal storage that may take the place of a fuel, take the form of a fuel, or as you mentioned, some kind of electrochemical battery that has a sufficiently low self-discharge rate that it can hold energy for 6 months and only get discharged once or twice a year.
I, I guess what it's I think we're saying the same thing because it's with traditional photovoltaics, their efficiency was so low that for you know given the natural tilt, the seasonal tilt of the Earth, you really had to store for summer to use in winter. But if you have high enough efficiency, which is what you're talking about, um, solar is effective even during low insolation parts of the year that you don't need to store from summer. And it sounds like you're saying about 95% of the time. Is that about right?
No, I think we are saying two different things. So the the need for seasonal storage is in no way affected by the efficiency that we're talking about in this paper. Like the need for seasonal storage just has to do with the fact that, to your point, the solar insolation decreases during the wintertime. There that fundamentally that means you get less energy, and there's nothing, even if your efficiency was 100%, that wouldn't change. The fact is that the demand is, you know, what it is in the wintertime, and you have less input from the weather during that time. So fundamentally, you have to store more energy from the summertime to use in the wintertime, no matter what you do. So I think the need for seasonal storage is a requirement that simply comes from the fact that the amount of sunlight we get changes throughout the year. What this efficiency has to do with is what we call the round trip efficiency, meaning you put in a certain, let's say, 1 joule of energy to charge up the battery. What fraction of a joule are you going to get out on the other end when you discharge it back to the grid? And so this efficiency has to do with that quantity, and which plays an important role in how storage integrates with the grid, but it doesn't necessarily in any way affect the requirement or the need for some form of seasonal level storage.
Couldn't this be
Thank you.
couldn't this easily be stored underground, or is there some sort of reason why storing it underground would be prohibitive? Because I think you could maintain perhaps more consistent temperatures year round if there was an underground facility. So yeah, that's kind of.
Yeah, it's a good question. So in short, if we could, we don't want to put it underground. The major reason we don't want to put it underground, although to your point, yes, the temperature is more consistent, but that's not really what we care about. The Earth is a better heat conductor than air is, or gases are. So for us, it's better to shield the whole thing with gas, and insulate the system with the one final layer of actual gas environment around the system, than to have it in solid contact with something else like the ground. So you lose more heat to the ground than you would to insulation and then surrounding gas.
Oh,
So,
Can I
okay. That's very
well,
counterintuitive. That's interesting.
so I
can I
have a,
comment on? Oh, go ahead.
well, let me get right to you, Dan. I just have a question about, well, two questions. So, in terms of the method, you have liquid tin alloy as your liquid metal. Graphite is your main heat storage, and you've got as you're pumping the liquid tin, you've got your photovoltaic and a gold reflectant around there. Is that essentially the? Is that correct?
That is correct.
Okay. I think that's fascinating. By the way. In terms of the efficiencies, in terms of application, are there? I'm sure there's critical scales where it makes sense. You mentioned the volume and the surface to volume ratio for the heat. Are there sort of family farm or home scales that could be appropriate, or is this truly industrial sized, larger community application?
Yeah, it's a good question. I mean, of course, as we scale up, we will be building, gradually building larger and larger systems. The short answer to your question is the bigger the better. The bigger it is, the lower the cost it is. So it's always going to be more favorable to make it huge. There is a scale about 50 megawatt hours that we envision, where we will probably be very competitive with other options at even larger scales. So for situations where someone wants a smaller installation, we will probably still be the cheapest option. But in general, to solve the main problem we're trying to solve at the utility scale, we want to go huge. So we're envisioning building 1 gigawatt hour scale batteries, which is like 100 megawatts times 10 hours of storage. That's enough to basically power, roughly speaking, like 100,000 homes for 10 hours, kind of
So how
thing.
many Star Wars destroyers is that? Because that Elon set that standard that now we count in those units.
Yeah, I'd have to get Star Wars destroyer converted to joules. I don't know how many joules a Star Wars
Go,
destroyer.
go ahead,
Yeah,
Dan.
so I'd like
There'll be
to.
a website
Yeah,
somewhere
I
who's done
wanted
that
to
already.
comment on the previous point about winter time. Needing seasonal storage. So, and if you take a look at the study from rethinkx.com, think tank that looks at this stuff at disruptive technologies, they say that the price of solar is getting so cheap, and it's cheaper than storage, that what we need to do is build 4 times more solar than or wind for that matter, than we normally need. So then in a cloudy day in the winter, we still have 100% of what we need, and therefore we don't need storage, except for overnight, of course. And of course, the 80% of the time when it's not cloudy and it's sunnier, then you actually have lots of excess energy, which you can use for things like decarbonization, desalinization, hydrogen production, or even Bitcoin and things like that. And so the numbers work out, and they run them, of course. So they're assuming that the price of solar continues to fall as it did in the last decade, and by the end of this decade, building 4 times more solar than you need would cost as much as building 1 times the amount of solar that you would use today, and therefore that will beat out. And they therefore say you don't need seasonal storage at all when you look at the problem that way. Thanks.
That's a great point. But I think the harder problem here is convincing policymakers, because the engineering, yeah, it's very understandable. Obviously, a no-brainer. I'm just saddened, for example, by my province here in Canada, which will be increasing the fossil fuel output because they're going to go gas for electricity, not solar power. So I don't know what other than reason we could use to help these people understand. But that's a harder problem than the science or engineering at times.
Well, I think they're arguing, by the way, you can take a look at it on their website, but they argue actually it doesn't have anything to do with policy. It'll be the cheapest form of energy, period. And so private companies will go that way. And it will be 100, it'll be 24/7, 365 energy. By the way, they do have, if I remember correctly, it's depending on the location, of course, it's somewhere between 30 and 90 hours of storage to handle the overnight and some of the other stuff. But then you don't have to go beyond that. And 80% of the time you have 2 to 3x the energy you normally need. So you have incredible amounts of excess energy, which is, you could say it's free since you built the system for the 24/7, 365 number that you normally need to meet demand. So anyway, it's pretty interesting, and I think if they're right, it means there's a revolution in renewable energy 10 years from now. Thanks.
Yeah, I think that is one interesting scenario where it'd be great if it can play out that way, which would nullify the need for, as you pointed out, a seasonal storage option. Um, Seasonal storage targets are extremely difficult to hit because you only discharge once or twice a year. Um, but yeah, I mean, if we can get the cost of PV and wind much lower, then yeah, then just dealing with the nightly and weekly variations may be sufficient, and hopefully our technology will be all that is needed.
Doctor, can I just thank you very much for an absolutely fascinating talk? This is really, really interesting. And can I throw a couple of layman's questions at you, if that's okay?
Yeah, sure.
Okay, well, first of all, I know this will be asked by members of the audience because it always is you mentioned there was a book that you were given when you were interested in how the atoms moved and everything, and you were given a book on molecules. Can you please, do you remember what that book is at all for us?
Yeah, give me a second. Let me just remember the author real quick. Hold on a second. I remember the title was "Understanding Molecular Simulation." I think don't want to mispronounce the author's name. Uh, Dan Frankel. Yeah, Understanding
Dan,
Molecular Simulation from Algorithms to Applications.
understanding molecular stimulation
From Algorithms to Applications by Dan Frankel. DAAN
rhythms.
Frankel,
Excellent.
FRENKE.
NKEL.
Frankel.
Excellent. Thank you very, very much. I know there's be more than one of us, more than a few of us will be looking this up by the end of the night. So thank you. My next question for you, please, was when I was looking up this photovoltaic effect was absolutely just fascinating. I've never heard of it. I've never heard of this before. I mean, obviously, I'm aware of the solar panels, but the first question, because it's like a two-parter. One, how does it use? How does it manage to use infrared to actually create electricity? And second part of that question is, does that mean like ultraviolet is not useful in any way, or can be useful in some way, and if not, why not? Thank you.
Yes. Okay. So yeah, this is an easy one. This is a softball question. So, um, the photovoltaic effect is, by the way, what Einstein got one of his Nobel prizes for. Um, and so the photovoltaic effect it's identical. It's the same exact thing that's happening in a solar panel. There is nothing particularly special in physics about the visible spectrum that we can see from the sun. Our eyes are evolved to see in the exact. It's peaked in the same wavelength range that we can see that the sun's radiation is peaked at. So the same effect can work at lots of different wavelengths. You can make a photovoltaic cell for far infrared. You can make it for infrared. You can make it for red light, visible, UV. You can make it for any wavelength you want. What changes is the voltage. So the frequency of the light, which is related to the wavelength. So as the wavelength gets shorter, the frequency gets higher, and the amount of energy in each photon is increasing. So the higher the frequency of the photon, you take the energy of the photon. So you take the frequency and multiply by Planck's constant. That gives you the energy of a photon, and that energy corresponds to the voltage that you will get from that photovoltaic. Or let me say, it corresponds to the highest voltage that you can get from that photon. You can absorb extremely high frequency photons in a low band gap cell. You'd be wasting a lot of energy doing that. Or you can use higher band gap materials and get it out at a higher voltage, which is more efficient. That is also, plays a big role in how our thermophotovoltaic cells reach the higher efficiency as we push the band gaps up and got the voltage up higher than what people have been doing in the past. And it works that way because our heat source is so much hotter. Um, we have more photons at high frequency that we can convert, and therefore we can do it more efficiently.
Thank you very much for clearing that up. That's totally fascinating. Thank you very much. For the next person, and feel free to ask.
Yes, thank you so much for fascinating work. And my question is about, internal recycling of the luminescent photons as well as the low energy photons. I was just wondering, in your model, as long as you talk about the TPV, you consider it this part, and if it's yes, how?
Can you say the last part again? You were asked about photon recycling, and then what did you
Yeah,
say the
I
last
was just
part?
wondering about your model and your work, and did you consider it that? And if it's yes, what was the efficacy and how you just reach out that?
So we don't necessarily get photon. I guess you could call it a luminescence effect. I guess we don't really track it in that way. I guess the way I think about it is, for an object at a given temperature, um, we always know, the material will establish an equilibrium with the electromagnetic field. So there will be a certain excitation of the electromagnetic field, a certain number of photons coming out of its surface per unit time, per unit area. And that's simply a function of the fact that it's at a particular temperature. So we have a bunch of photons coming out that we cannot utilize, that we don't want to convert because they would convert at a low voltage and be inefficient. So we reflect those with a mirror, we send them back, and their purpose is to help keep the object hot so we get a steady stream at high rate of the high frequency photons that we actually can convert very efficiently. So if we did not utilize those lower frequency photons, um, the only problem with having them be absorbed and not utilized to make electricity is that they would then help to cool, and they would detract from keeping the object that's doing the emission hot.
I see. So, I mean, technically, we have still the trap photons, right, at the beginning. So,
Yeah, in a sense, the photons are being emitted by the hot side, reflected by the mirror, reabsorbed by the hot side, and then, the question now, I think sometimes the way people frame it is like, so where did that energy go? Well, right, it goes to it goes towards keeping the object hot. You could try to draw a line and say, okay, well, I'm going to follow the path of that photon, and maybe that photon, after it converts to phonons, then comes out at a higher frequency, and you imagine it like you're keeping track of the same energy. That's one way to look at it. But in general, I just look at it as an energy balance between an object at a particular temperature. You get a steady stream of photons because it will establish equilibrium with the electromagnetic field.
I see. Very interesting. Thank you.
So you mentioned you started a company. How's that going? I mean, are we going to see commercial deployments? What's your timeline on this?
I would expect to hear hopefully something really exciting in 3 years from now, after we build a first pilot demonstration, and then we will be moving swiftly to commercial deployment right after that. So we've been building this system in my lab at a small handheld scale for the company. We're now moving to building it large enough where you need cranes and forklifts to move the components around. Once we demonstrate like the repeat unit, the actual thing that's going to get repeated throughout an extremely large system, then if we get this now subsystem to work properly and be reliable, then we'll be scaling it out, meaning making lots of them as one large system, and then that'll be we'll hopefully have a revenue generating deployment of it about 3 to 4 years from now. But the company's going well. We are, it's called Thermal Battery Corporation. I'm going to get the website updated. Their website that's there now is like a placeholder, but there's something you can at least see it. You can sign up on our contact form and get emails when we have updates about how the technology is moving forward, and we'll be happy to let everybody know how it's panning out.
That sounds great. You said you were at 40% efficiency, but you said that you can imagine 50% efficiency being within your grasp in the future. Do you have any kind of like reasonable expectations of how high efficiency could be achievable in the
Yeah,
future?
I expect that we will get to 50% at the end of this next 3-year project. So that's part of the project that we're scoping out, is to make the next set of improvements that'll get us to 50%. I do not anticipate that we will get far above 50. We may get to 51, 52 if we, over time, but I don't expect that we're going to get to 60 or 70 or anything like that.
Is that because of the kind of restriction that you're dealing with without like basically an unforeseen breakthrough? Without one of them, it's not likely to go much higher than that?
It's actually in some ways related to the second law of thermodynamics. There is a kind of fundamental limit on the maximum voltage you can get in a photovoltaic device that's related to the second law. It just has to do with the fact that the cells themselves are at room temperature and they're not at absolute zero. So by virtue of the fact that the cells are at finite temperature, the cells themselves are emitting photons at long wavelength infrared photons, and there's what's called a radiative recombination rate. So there's a certain probability that an electron you excite with the light that is coming from the battery will recombine and manifest as wasted heat, and you kind of can't get around this limitation. you can you can do the best you can, and I think the cells we can get do a really good job. But there's like a intrinsic limit on that, on how well you can do with that.
Interesting.
Maybe
Thank you.
maybe a side question. The sensors we use metamaterials, which kind of just vary the geometry or the collection, the pattern of atomic structure on the surface, and you get some improvements. Do you, I guess, would you say you're already using that sort of concept, or have you explored that in any way?
Yeah, we're definitely already using that concept. That's part of how we got to the 40%. These are 3,5 indium gallium arsenide cells that are grown on single crystal substrates with extremely high device quality and very low defects. So that's a big part of how we got to the 40% in the first place. There's still some additional improvements to make, but device quality is definitely one of the ones we're pretty far up on the curve on, or let me say pretty far down on the curve in terms of improvements. I don't know that there's a whole lot of extra improvements we'll make in that regard.
Yeah, unless of course those UFO crafts, UAPs, all that stuff actually turns out to be true. That would be rather interesting, as that's a topic that comes up with those discussions, the metamaterials, and so it's been a pleasure hearing you talk about this, and quite interesting that we could use something like a liquid metal to store energy. Just the ways that humans are innovative is just quite fascinating sometimes. So thank you.
Well, thank you.
Thank you so much for answering all those questions. And I'm really apologize if this question is really stupid, but you mentioned before that trapping photons more efficiently. This competitions for artists to make the darkest, like the blackest black you can get. Is there a way to utilize that blackest black and what artists come up with to trap more photons, or is that just silly, basically?
So there are no stupid questions. This is an interesting concept. In short, um, probably not from a practical standpoint, but in principle, yes. So, yes, it'd be nice. We don't really have the problem of needing to absorb more photons. Like, the easiest way for us to do that is simply to make the device thicker. So, um, we actually forego absorbing all the photons on purpose. So we actually like it to be partially transparent. There are a number of advantages and reasons we do that. Um, but yeah, I mean, in principle, yes, you want to absorb a lot of photons. Anything above the band gaps you want to absorb, and everything below the band gaps you want to be transparent to. So in principle, yes, but in practice, probably not. We don't really need to do those kinds of things because we have a very easy knob to turn that we can absorb more light if we want to.
Yeah, the scale of this problem reminds me of these water batteries, where it's just a dam that stores water over a certain altitude, and then they just let the water run. When they need electricity, that powers the generators, and then they refill the generators. But these things are huge, like just the scale of these things. You would never think that a battery would be the size of a lake.
Yeah, I mean that's as so what you just described is what we call pumped hydroelectric power. It is generally speaking the only real form of storage that exists on the grid, but there's not very much of it. Um, it does exist, and it's restricted geographically to certain locations where you've got two bodies of water that are at different heights. It's Our battery technology is slated to be cheaper than that, and so um, pumped hydro has the problem of being geographically limited in addition to not being cheap enough, and we're hoping to um, do better than that by being geographically unlimited, where we can put it wherever, site it wherever, and also cheaper. So, but that is the scale that we're talking about in terms of.
But on the question of safety, I recall. one of these professors who was working on liquid metal batteries said, the military asked him what would happen if the casing or the structure was penetrated. Well, the metal would just cool down, and their response was, "Oh, so it's battle hardened." Can you comment on the like the safety? Because as people think about who to elect or whatnot, if those people can comment in some way about the safety, that would also be a good way to reinforce the argument.
Yeah, that's a good question. So, from a safety perspective, there's no fire hazard. So, one of the major reasons we chose liquid tin and not one of the many other liquid metals that people have looked at in nuclear is because it does not oxidize very exothermically or violently. So we routinely deal with liquid tin in my lab. It's just like, you know what it is? It's like solder. So tin is the main element in solder. So you can melt solder and it doesn't explode. Um, there are other metals like sodium and the alkali metals that if you melt them in air, they immediately catch on fire and explode. So tin is not an explosion hazard. The graphite is also not an explosion hazard and not a combustion hazard. The materials that we're using, the graphite is sufficiently dense that it will not combust. If it were to, let's say the containment of the system, which keeps air out, if that were to break, let's say, I don't know, somebody detonates a bomb next to it and all of a sudden air is able to get to the system, it still wouldn't explode. It also wouldn't catch fire. The graphite we're using is too dense, so it does not have enough surface area per unit volume to really catch on fire. Um, and so it won't combust. It would gradually oxidize, so it would gradually disappear, particularly the insulation. That's the first thing that will go. But it will not actually like catch on fire and be a fire hazard. You don't need to come put water on it per se. Um, there are no hazardous chemicals used, so none of the components. I mean, which basically the entire thing is made out of carbon and tin, which are both fine in terms of safety. You can hold it in your hand and not die. Doesn't make you sick. Graphite, for the most part, is basically like pencil lead, so it's the same stuff that people are exposed to all the time. There's nothing special about it or hazardous about it in that respect. So the only, I guess, sense of a safety risk has to do with, this is not something we would just put in the middle of a city where random people could walk up to it and possibly get into it. This is something you would site outside of a town or out of town a little bit away where it's an industrially managed location facility, similar to like a chemical plant where you have specialized people with who've undergone space safety training that operate it and are exposed to it. Again, as I mentioned, the whole system is held inside of a warehouse that has inert gas. So there is a asphyxiation hazard there in the sense that you can't just walk in and touch the battery because there's no air. So you wouldn't be able to breathe. So sending people in to actually work on it will require specialized training and equipment to be able to go in and work on it while it's hot. But other than that, um, there's no fire hazards, no safety hazards with regards to the community. If the liquid metal starts leaking out, this point you made is exactly what would happen. The liquid metal will start dripping and working its way through the insulation. As the insulation cools, it'll eventually freeze inside the insulation. So it's not like you get a big liquid metal pool that starts pouring out all over the ground somewhere.
Thank you. Yeah, I wonder what it would look like from the inside of what I assume would be some sort of crazy spacesuit of some sort. You would need to work in those areas, so perhaps that would be an interesting challenge to overcome. Sounds like some graduate student in the future or some other project manager. But yeah, thank you. Thank you for commenting on the safety.
Yeah, thank you.
And can I just say, personally, I think the thought of you working with loads of liquid metals just sounds so cool. It completely always makes me think of the T-1000 of the old Terminator movie, the liquid metal stuff.
Yeah.
Um,
Yeah,
and and
it's actually so tin. One interesting thing, I think there's maybe some YouTube videos and maybe there may be a picture. I think on the that I put up on the website, you can actually see a picture of us flowing liquid tin at 1400 C. One thing that was a little surprising when we first did it is the tin. Even though the graphite is glowing white hot, even when the tin is that hot, it's still shiny metal. So you can't tell how hot it is by looking at it. It's actually extremely hot, but it's still shiny like a mirror.
that is so cool. Also, we're very aware that we want to be respectful of your time, and that's been an hour and a half right now. How much more time do you have with us before we have to let you go? Because we do want to have you back if you're willing in the future, so we don't want to exhaust you.
Yeah, sure. I got probably another 5, maybe 10 minutes. My kids are wrapping up pretty soon.
All right, that's cool. We'll just take a couple more questions. Is that okay, Katerina?
Yep, that's perfect. Thank you.
Okay, who would like to ask the final questions then? Just flash your mics, please.
Sorry, could you hear my answer? Because I got a phone call in the middle. So.
I heard you say, yep, no problem. Yep. So if anybody wants to ask the doctor any questions, just please come and speak up.
Let me just circle back on the commercial scale out of the. Could you repeat again what the name of your company is? Thermal Batteries.
Thermal Battery Corporation website
Thermal Battery.
is thermalbattery.co.co.
Okay, great. So, what is the? Can you tell us the scale of your first commercial deployment?
Can you guys hear me still?
Yeah, we can hear
Okay,
you.
sorry, I got a phone call came in.
Are you able to answer, or did you hear the question?
Yep.
Oh, I'm sorry. Maybe I missed. There was a question. I apologize. A phone call came in and it cut me
Oh,
off. So
yeah.
I
No, I'm
apologize.
sorry. I just asked about, in terms of the company, you mentioned 3 years. Is there a target scale for your first commercial deployment?
Yeah. You mean the one we're going to do during this 3 years, or are you talking about what comes right after?
Oh, both, if you have answers for those.
The one for this next 3 years is 1 MWh. We've chosen that. There's a lot of thought that went into that number. What comes right after the 1 MWh could be anything from as low as probably 10 MWh to a few hundred MWh. So it'll really depend on who the customer is and what they're willing to pay for. The other benefit, though, of thermal batteries is that they're expandable. So we could, for example, someone could treat it as high risk and we could build a first 50 MWh. Then if it looks like it's working fine, we could then go add to it and add another 50 MWh or a few hundred MWh. It's expandable, so you can still utilize the existing infrastructure and gradually build out the amount of capacity and storage. So you could say, build a 10 megawatt battery that can operate for 5 hours, then say, okay, that works well, let me add another 5 hours and have it operate for 10 hours. Then you can say, let me go to 30 hours or whatever. You can keep adding on and still use your 10 megawatt power cycle.
And do you have scaling parameters for, for the given height of your system, the area of the battery versus the area of the solar field in order to support it?
Yeah. So yes, in short, so the height is what we're trying to work out now in this first 1 MWh battery, meaning that's the main variable we're trying to hold constant as we scale out. So we're going to build a battery that has the full height that you would see at 1 GWh, 10 GWh, whatever it is. Like, we don't really intend to really change the height much. So we want to build all the components at their same dimensions that they will be at an extremely large scale. But we're going to build a subunit that is one repeat unit, and we will build units that are larger that have hundreds or thousands of them inside of it. Um, I hope that maybe somewhat addresses your question. I forget how you worded the question. So.
Oh, the corresponding increase in
Oh
area
yeah,
of the
yeah, yeah.
solar field.
It's a pretty dramatic difference, right? So we've actually done a little bit of work on this recently. So let's say you want to bundle a solar field along with a thermal battery and make that PV plant act as a totally dispatchable resource for the grid, where now it's truly dispatchable renewable energy. The utility grid can call in and say, we want X amount of megawatts at this time tomorrow. And it can be at night, it can be in the morning. It's decoupled from when the sun is up. And so what you might do is you might build a 100 megawatt PV field. PV is nominally about 200 watts per square centimeter. So if we multiply by 5, that's a kilowatt. Then by another 1,000, so 500,000 square meters is how much PV area you would need. The thermal battery would probably be sized at about 15 megawatts. So you would have a 15 megawatt power plant now. That thermal battery would be a quarter of the size of a football field. So that's more like, that'd be considerably smaller. Sorry, give me 1 second. It's probably a factor. I haven't worked this out, so I'm just guessing here. I wouldn't be surprised if it's about um, 10 to 100 times smaller than the solar field. So it's very compact and very small by comparison to the amount of solar you have to put up to feed it. They could easily fit on site in a small corner somewhere.
That's wonderful. It's a great ratio. So it's still mostly the solar field land demand.
That's right.
And this can just store whatever the solar field doesn't use immediately.
Right. This is very small. This is a small add-on. It's comparable to the size of the grid interconnect that you would need. Like, I mean, it's like, the space that you need for the grid interconnect, like put a couple more interconnects and that's about enough for the battery.
Well, that's wonderful. Certainly look forward to many deployments.
Yes, me too.
Katerina, are you there? Yeah.
So are the 10 minutes over? I lost track. But anyways, you answered so many questions, so I think you must be tired of us by now. And thank you so much. This was such an amazing talk, and it's so important work. So I wish you all the best, or we all wish you all the best for your company, and hopefully you'll get all the funding you can get and the least bureaucracy, and that everything works, because the world needs your technology and your work. So we are all cheering you on here. And if we can do anything, I don't think I can, but because I'm too, it's not my expertise, but we are here.
You can definitely help, which is spread the word and let people know that this technology is on the horizon. Call your senators, call your representatives, and demand that they put government funding behind it, and call your representatives and senators and start demanding a carbon tax. Those are the things that you can do to help.
Definitely, we totally are for that. And and we will, do our best to help spread the word. And if there's anything we can do, let us know. And if you have any updates, or if you want to come back at any time, also let us know. We are always happy to have you here. I think we all enjoyed this very much and learned very much. So I really appreciate it, and we all do. And thank you everyone for coming and asking questions and helping out with this room. So thank you. Go ahead, Jane.
Just going to say thank you so much for your time, Doctor, and I would love for you to be able to come back when you've got some more updates for us, because this is very exciting. And if we have any speakers that we think could help you along in your project, we will steer them your way, because
Thank you
we've
so
on
much.
more than one
Oh,
occasion
sorry, Jamie. Sorry.
had a little collaboration. Yeah, sorry, Victoria, go for it. Yep.
Well, I appreciate you all inviting me. Thank you for the opportunity. And, I advise and recommend anyone that's interested in keeping up to date with what we're doing, if you can run over to the website. I think it's a fundraising contact form. You can fill it out. I'll use that as a way to build up an email list and keep you informed. I'll probably do some kind of webinar at some point to update anyone who's interested or an enthusiast who wants to support on what it is that we are working on and how it's going.
Great, we are looking forward to it. And yeah, please all visit the website and yeah, call your senators, make funding happen. And the carbon tax, I think it's probably one of the most important things we can have to survive on this planet. Yeah.
All right. Thank you all so much. Appreciate it. And I will hopefully hear from you again at some point. Talk to you later.
Yeah, thank
Yeah,
you so
Thank
much.
you very much, Doctor.
And enjoy your weekend. Happy weekend.
Thanks so much.
Yeah,
Nice
and
to
thank
meet you, Dr. Henry,
you
and for
everyone
knowing
for
about
coming.
derivatives.
Maybe I just have the delay, so I kind of speak over people. I'm really sorry.
No, I'm hearing Victoria's got a bit of a delay, I think, as well. I'm hearing it too, so that's okay. We've all got it. It's okay.
Okay. Yeah, thank you all for coming today. I really appreciate it. Thank you for helping with the room today. And yeah, this was such an interesting discussion and topic. And if you like discussions like this, please follow the club. We will have more rooms next week. Maybe we'll have tomorrow kind of a more roundtable discussion updating on our science news, what we want to, maybe who we want to invite next, interesting science papers that came out, and then Sunday we'll have our weekly recap, and on Monday we'll have Dr. Hildebrand talking about sex differences in pain signal processing and how to come up with treatments that work for both for male and female, because that was not done before. Then Dr. Ballaston is talking about how he came up with an individualized targeting of TMS treatment. So TMS is like a novel type of treatment for mostly used for depression and anxiety disorders that are untreatable with drugs, and it's been working quite well. But to make it even more efficient and maybe spread out to more disorders, an individualized targeting for each region and individual is really important. So we will be talking about that. Then we'll have Dr. Katia Paglia here talking about massive gravitons and if they are good dark matter candidates. And Dr. Moses, he will talk about this very prominent research that came out lately about a BCI for decoding speech and paralyzed people, so that they can communicate with the world. And on Friday, we'll have Dr. Lupora talking about artificial 3D printed robot skin that feels just like humans. We talked about this in Tyler's room actually the other day, Eric, right? Yesterday, I believe. And then, yeah, that's the next week. So, yeah, it will be another exciting week. And come back maybe tomorrow for like a more roundtable science discussion. And thank you so much, everyone, for coming.
Thank you very much, Katerina. Good night, everybody.
Bye.
Thanks, everyone.
I'll close the room in 3, 2,
Good night, everyone.
bye.
1, 2, 3,
Happy
go
Friday.
science!
Go science.